So
Okay.
everyone, good morning. So I'm very happy that the AOGS Society also helped us to distribute this talk to the colleagues for the astronomy community. Thank you for Professor Liu. My name is Charles Lin, represented the Taiwan Space Union. So today we are very happy to have Dr. Young-Sil Kwak from Korea Astronomy and Space Science Institute to share the recent update of the Korean space mission for space weather research. So yeah, go ahead. Young-Sil, it's your time.
Yeah, thank you so much for my introduction. So sorry again. Okay, good morning in Taiwan. I'm Young-Sil Kwak from KASI. First of all, I'm very honored to be invited to speak at the TSU PRISM seminar. Although it is online, it's a great pleasure to meet you through this seminar. Today, I'd like to introduce space missions in Korea for space weather research. Okay, the sun is the center of a solar system and the source of all life, as you know. The sun is quiet when we see it with the naked eye, but in reality, it is constantly active. Especially when there is very intense solar activity, such as sunspot explosion. Enormous amounts of energy are emitted from the sun, including strong radio waves, magnetic field, and billions of tons of high-energy particles pouring into the space of the heliosphere. Such intense solar activity causes rapid changes in the Earth's manosphere and upper atmosphere, and the high-energy particles ejected from the sun reach directly into the Earth's upper atmosphere, causing aurora in the polar regions. Environmental changes that occur in space are called space weather. As you know well, sudden changes in space weather caused by strong solar activity cause enormous damages to humanity, including malfunction of satellites residing in the space around the Earth, damage to satellites, disruption of satellites communications or terrestrial wireless communications, increased GPS errors and damages to the terrestrial power grid. It also poses a significant risk to human space activities, affecting the safety of polar route crew, passengers, and astronauts. As humidity becomes increasingly dependent on numerous cutting-edge technologies, damage from space weather changes increasing. In order to minimize the risks and damage caused by these sudden changes in space weather and protect the safe lives of humanity, it is very important to understand, monitor, predict, and prepare for solar activity and changes in space weather. So, to meet these demands, the KASI, Korea Astronomy and Space Science Institute, has been building and operating a number of ground-based facilities to observe the sun and near-Earth space weather since the establishment of the Korea Space Weather Research Center at the KASI headquarters in Daejeon in 2007. In preparation for the globalization of satellite and communication networks and the era of space exploration, KASI is carrying out a project to establish a global space weather observation network and conduct research on changes and the predictions of space weather up to the heliosphere. Especially KASI has been developing various satellites and payloads since 2017 to observe space weather from space. This time I will introduce briefly space-based observations of KASI. Okay, first I will introduce the CODEX mission. CODEX means coronagraph diagnostic experiments. CODEX is next generation solar coronagraph development mission to observe the coronal mass ejection phenomena during solar activity that causes space weather changes from the ISS, International Space Station. CODEX uses multiple filters to simultaneously observe the temperature, velocity, and density of the coronal region over 3 to 10 solar radii. This will be the first in the world to simultaneously provide the temperature, velocity, and density of coronal region 3 to 10 solar radii. CODEX is being jointly developed by CASI and NASA. CASI is in charge of main electronics, polarized camera, filter wheel, and flight and ground software. And NASA is responsible for installation and operation on the ISS management and optical and mechanical assemblies. The CODEX launch is scheduled for September this year, and it is expected to operate for about 2 years after construction on the ISS. This photo is CODEX being developed at the NASA site. It is scheduled to be moved to Houston launch site later this month, and the launch is scheduled to be by SpaceX. For reference, 3 steps were taken to develop CODEX. Total solar eclipse test observation in 2017, balloon experiment success in 2019, and ISS installation this year. Okay, next, SNIPE mission for ionospheric research. SNIPE means small-scale nanospheric and ionospheric plasma experiment. Main mission of SNIPE is to elucidate small-scale 10 kilometer to 100 kilometer plasma structures in the topside ionosphere through multi-satellite formation flight. SNIPE consists of 4 units, originally 4 unit CubeSats and the Dawn-Dusk Sun synchronous orbit at 550 kilometer altitude. SNIPE was launched in May 25th last year, and fortunately it is still operating normally. SNIPE has 4 scientific instruments. LANGMU probe to observe ionospheric plasma density and temperature, solid-state particle detector to observe precipitating energetic particles, especially electrons, flux gate magnetometers to observe magnetic disturbances, gamma ray burst monitors to observe outer space hard X-ray. Okay, SNIPE can observe space weather in detail through formation flying. Satellite distances and formation flying shape will be changed from 10 kilometer to 100 kilometer with a long track and cross track. A long track flying shape can observe temporal variation of a plasma structure, and cross track flying shape can observe spatial variations of plasma structure. Okay, SNIPE science objectives are as follows. First, a spatial scale and energy dispersion of electron microburst, temporal and spatial variations of plasma flow, temporal and spatial variations of electron density and temperature in polar cap patches, coherence lengths of bob, flap, and MST-IBS, and large amplitude disturbances of field line currents. This shows the SNIPE bus system. The left panel is exterior, and the right is the interior. There are the solid-state telescope, Mac, thruster, and the GPS antenna, other payloads, and other things for the SNIPE in interior. Okay, this shows the SNIPE assembly. The left shows a near-Earth space environment observation satellite assembled in the clean room environment. The right shows the 4 near-Earth space environment observation satellites flight model integrated in the clean booth. We constructed a SNIPE ground station consisting of 1 UHF antenna and 2 S-band antennas at CASI. And we established the Mission Operations Center to control satellites at KASI. Okay. The SNIPE satellites were transported to Naro Space Center in Korea for launch on May 4 of this year, last year. The left shows the satellite ejection tubes. The right panel shows putting of 4 satellites into ejection tubes. Okay, SNIPE was launched on May 25th last year on board the domestic launch vehicle Nuri. The left shows the launch, the middle shows the separation of SNIPE P, and the right shows the separation of SNIPE D. Unfortunately, SNIPE C could not be separated. This shows 3 satellites of SNIPE. If you click here, you can see the current orbits of the 3 satellites now. This shows an example of science data from Young-Sil probes. Upper panel shows electron density, and the lower panel presents electron temperature. From these examples, SNIPE B Young-Sil probe successfully observed a typical dust side equator ionization anomaly and the morning overshoot. So these days we are gathering all Young-Sil probe data. And next one is example of science data from solid state particle detector SST. Left panel shows SNIPE B SS data, and the right panel shows Van Allen proofs data for radiation belt. From these examples, SNIPE B Young-Sil probe successfully observed the typical S-shape morphology of the slot region of radiation belt. This shows an example of a science data from magnetometer MAG. The black, red, and blue lines represent X, Y, and Z components of the magnetic field, respectively. In order to achieve the scientific goal of SNIPE, simultaneous ground-based observations will be very effective. So, comparison will also be made with IceCat, polar regions, and the low and middle latitude ground observations. Okay, next, rockets. Rockets means Republic of Korea Imaging Test System. Rockets, not rocket, rockets. Okay, as you know well, optical observation of aurora from the ground provides high-resolution images, but has weather and space limitations. Existing satellite observations provide information on the extent of the area where aurora occurs, but the local time observed by the satellite does not match the time of nighttime area near midnight, when aurora activity is active, and spatial resolution is low. So, satellite observation with a high resolution is needed while showing the form and range of aurora that occurs over 1,000 kilometers. So we started thinking about developing these rockets. Okay, our rockets is a spaceborne wide-field auroral air glow imager, and the main payloads to be carried on the CAS 503 satellite. Rockets has field of view with a 90-degree and synchronous orbit at around 600 kilometer altitude. Observation wavelengths are O1 green line and red line with a 3 nanometer filter bandpath and visible without bandpass filter. Observation targets are aurora and atmospheric gravity waves. Rockets will be launched in late next year, in 2025. Rocket's main payload to be carried on the CAS 5003 satellite. This CAS satellite is a spacecraft platform for small satellite mission, and is dedicated to space science and technology demonstration. This satellite will be launched early next year and onboard the domestic launch vehicle Nuri. So secondary payloads of this CAS satellites are IMF for Langmuir probe and magnetometer, and the biocabinet for 3D stem cell culture and printing. Our rocket has two goals. Science goal is understand the response of the ionosphere, thermosphere system to external and internal forcing. Objectives for this goal is to identify the auroral oval boundary and auroral shapes in the visible wavelengths. And technical goal is demonstration of the all-sky image of performance from space through observing gravity waves and plasma bubble. Okay, this shows rocket system. Size is 420, 650, around 300 millimeter. O1 green line and the red line cameras are inside, and the visible camera in the center. This is onboard computer this here. Right panel shows optical layout. So this rocket's camera consists of 9 lenses. Okay. This shows assembling and testing the developed rocket's camera. So that testing institute is very far from Daejeon. So it takes 3 hours from Daejeon. So this is so frequently. So we are testing and assembling. Yeah, they're long distance institute. This shows rocket's operation concept. Rockets primarily toward the nadir during observation in night side. In day side, satellite aligns with the sun. There is a sun pointing. During reorientation from sun to nadir pointing, rockets initiate the imaging process and at this time carries out the limb observation of aurora. Okay, the Korea Polar Research Institute conducting aurora observations through an all-sky camera ground observation network at the Jangbogo Station in Antarctica. So rockets observations are evaluated through joint observations with the Jangbogo Station observations. We also plan to study the evolution of auroral structure with this collaboration. And we aim to investigate auroral boundaries in visible and FUV wavelengths using rockets and DMS-SUSI simultaneous observations. Additionally, we plan to collaborate with Johns Hopkins APL to conduct research to secure the entire aurora boundary based on the partial aurora images. Okay, as science applications, we plan to study equatorial plasma bubble phenomena, a typical phenomena in the low latitude ionosphere. Rockets observations enable us to track the evolution of plasma bubbles from the magnetic equator to higher latitude filling data gaps at the intermediate latitudes, as shown right panel. In the future, we expect to able to conduct collaboration research with international scientific missions on the ionosphere and upper atmosphere, such as EZ, tracers, and GDC or dynamic missions of NASA. Okay, I'd like to briefly introduce 2 new missions currently being planned at KASI in Korea. Okay, first one is Athena. We are developing Athena as a new mission for ionosphere and atmosphere. Athena means aurora and the thermosphere, energetics, neutrals, and atmosphere. Athena will fly an enhanced version of rockets and an FUV imager. Athena will provide visible near-infrared and ultraviolet imagery of the aurora and the Earth's upper atmosphere to study the response of upper atmosphere to external and internal forcings. The picture on the right is an example of observation expected from the Athena in the future. So this shows, for instance, IR and FUV image observations by EPOP and the TMSP satellites. So EPOP results represent we can hope as Athena rockets image, and the TMSP SUGI results can represent the Athena FUV imager. So combination between these rockets and the FUV imager, so we can get good result for upper atmosphere energy or the auroral energy or internal and external forcing into upper atmosphere. And Athena will provide the key parameters needed for space weather and also meteorology. As secondary payloads, we are considering GNSS RO, metometer, Langmuir probe, and particle detector. And the satellite for this Athena is a small satellite. And we hope launch will be scheduled in 2031, 2032. Okay, next one is L4 mission for M2M, Moon to Mars. So as you know, for human activity into space, so radiation is very important and into our human activity. So CASI has granted the feasibility study of L4 mission for preparing the development of an international heliospheric observatory positioned at L4, not L5, L4, for innovative solar and space weather research and forecast. L4 mission aims to define the potential scientific exploration scope of the proposed L4 mission in the three areas. One is space weather, and second one is space radiation effects on human safety, and also optical space communication. And the Korean, currently Korean lead L4 mission and will produce unprecedented synergy for future human exploration of the Moon, Mars, and beyond. So, these days our country will open CASA, similar to NASA or JAXA or TASA. So this L4 mission, L4 mission will be frontier for this CASA activity. We hope. Okay, as a summary, SNI will celebrate its first year of operation in May, this May, and will observe space weather in detail. In the second half of this year, CODEX will observe the solar corona from the ISS. And next year, rockets will go into space on next generation medium-sized satellite and observe the aurora. Additionally, preparations for the Athena mission, which can observe the energy flowing into the Earth's upper atmosphere, and the L4 mission, which can continuously and free dimensionally observe the space environment caused by solar activity have begun, and the expectations are very high. Yeah, just we hope. So please increase Korea's space mission for space weather research, yeah, including CASI. Okay, that's all. So
thanks, professors. Amazing talk. So if anyone has any question, please turn on your microphone, or you can type your question in the chat box.
Okay, so if you have a question about our CASI or Korea space mission later, so please contact me. Yeah. So we are since 2017. So our CASI or Korea has been developing many missions for space weather research, and our CASA will also support strongly our part, especially space weather research. Okay, please distribute my email to audience. Yeah, please, and if you have questions so later, please send the email to me.
Yeah, I have some comments. Dear Young-Sil, should I? Yeah. I don't know if you know that IAG goals, we have a joint study group titled Space Weather Monitoring and Prediction. And we have experts in solar physics worldwide. Maybe I think these new missions and new observation would be very helpful for some cross validation and some space weather research for space weather events. Maybe we could discuss some collaboration in the future.
Yeah. So if L4 mission case, there is solar physics part. So these days, L4 mission development team is gathering international idea, such as NASA or other other institute or other university international.
So next time, if this group have an online meeting, I would like to invite you to join us.
Yes.
Okay. Thank you so much.
Okay. Thank you. Okay. My group is a little bit a big group. Yeah, the number of our group member is more than 35, almost 40.
Oh.
So our group is studying, researching about the solar physics, manospheric physics, and ionosphere and thermosphere, or lower, middle atmosphere. So we are working about some prediction monitoring, ground-based monitoring, and space-based monitoring, and especially CME prediction is very expert part.
Good to know.
Yeah.
Okay, here we see Lin Qihong. Lin Qihong, can you turn on your microphone and ask your question?
Thanks for your great talk, Professor. So I have one question. Is because the space mission in Friday also includes some satellite that contain an optical imaging system. But for satellite, usually a small satellite. My question is, in theory, for optical imaging system need extremely high precision because they need to scan a very long, far away Earth. So this kind of optical system in a big satellite usually is supported by the big scaffold system in order to prevent the deformation. But the small satellite usually didn't have enough space to contain for scaffold. So how can we package the optical system inside a small satellite but also keep their high precision imaging? So this is my question. Thank you.
Your question is about rockets, right?
Yeah.
Not small satellite, not a snipe, rockets. Right?
Yeah.
Yeah. So when we, I remember when we considered that rockets to observe high resolution. So we had also the same some question ourselves about that. That is very challenging to observe optical image in space. So our that resolution is 5 second, 5 second temporal resolution. So 5 seconds is very short. Yeah, very short. So we are considering about some analysis for that data staking the data, and some analysis process it will be helpful to extract that good image. So your question is okay. I can understand your question, but we also have that question by ourselves about to observe high resolution image data in space through our rockets optical system. So yeah, that is very challenging. But as mentioned before, so we are concentrating some analysis process, to gather data and some staking data and post analysis. The data, staking the data. So, and engineering meanings or other engineer part, maybe can answer about that in detail. So.
Okay, thank you, Professor.
Yes, thank you very much for your nice presentation. I would like to share also that the next IUGG General Assembly will be in Korea. I hope we can meet there. And also, I would like to make a small question because my research focus on thermospheric mass density, the neutral density, and if you had some idea on how to measure this density or which instruments we could use, new technologies, because nowadays we're only using accelerometers and GNS in the data.
Okay, you have a very idea. Yeah, so yeah, in the near future, so yeah, I hope to discuss about that. So
Next IUGG in Korea will be next year?
Not IUGG, AUGS.
IUGG General Assembly in 2027.
2027.
Oh, 2027. Oh,
yeah,
IUGG.
we host.
Okay.
We will host. Yeah. After 3 years.
Wow. So this year we have a AOGS and COSPA in Korea. And
yes,
3 years later we IUGG. That's excellent.
So you're pardon.
Any more questions?
No, there's no.
Oh, that's great. So looking forward to see Dr. Young-Sil Kwak in Korea soon in summer, and I hope that some of us will be in AOGS or in IUGG so that we can meet in person for discussion.
Yeah. I will meet both.
Yeah, it's very good that the status of the Korea's space development. So I would like to thank Dr. Young-Sil Kwak again. Thank you very much. And she's really leading the group for the space weather in Korea. So hopefully we can have a more collaboration with her team. Yeah.
Yeah,
Yes.
we really hope collaboration with Taiwan team and
And
yeah, thank
AOGS.
you.
Yeah.
And AOGS,
Yeah.
yeah.
Yeah. Yes.
Thank you so much, inviting me to your seminar. And
Great.
sorry again, starting is problem.
No problem. No problem. So thank you all for coming today, and I think we will also have a future PRISM presentation relative to our communities. We will distribute it to you. Thank you all again. So have a good rest of the day. Thank you. Yeah.
Thank you. Yeah. See you at AUGS or COSPAR.
Yes.
Okay.
Yes. Okay.
Thank you. Thank you.
So thank you.
Thank
That will
you.
conclude our. Thank you. That will conclude our webinar today. Thank you all.